controls your life. So right now, you probably think that you're just sitting still. But in reality, there are millions of cells whizzing through your bloodstream, forging hidden connections between every inch of your body. Sorry, if you stop to think about it, you can even feel this interconnectedness. For example, you know those butterflies you get in your stomach when you're feeling a little bit nervous about something? Maybe you're giving an important speech in front of a big audience. That's an example of something that is a purely cognitive experience, a thought, manifesting itself as a physical sensation elsewhere in your body. But how does my gut know what my brain is thinking? We have this tendency to think of our brains as the driver and our bodies as the vehicle, because after all, my brain can tell my body what to do. But in reality, this communication goes both ways. And when it comes to fast, reliable, and long-distance communication, immune cells are actually our most important messengers. Immune cells not only talk to each other, they talk to other cells in your body, including in your brain, and they even talk to the other living beings inside of us. Despite being best known for their job fighting off bad guys, immune cells have a host of different roles. They help to repair our wounds, they transfer information between organs, they change our behavior, and they even protect our consciousness against things like anxiety and depression. So it turns out, rather than just being a simple defense mechanism, our immune system is more like a spatial information network that can carry signals across our body, keeping everything in balance and everyone informed. One such information network that we've only recently begun to truly appreciate is something called the common mucosal immune system. Mucosal sites are the parts of our bodies that face the outside world. Think your gut, lungs, skin, etc. And because they face the real world, this is often where infections first start. In order to protect themselves, these sites have to communicate with each other about what is going on in the environment. And they do this in a really interesting way. When cells are activated at one mucosal site, like the gut, a portion of them know to move to other mucosal sites, like the lung or the skin, so that your immune system can make sure to have guards at every door into your body. What's even cooler, during pregnancy, cells will actually move from these mucosal sites into your mammary gland, and they can secrete immune molecules into the breast milk, effectively transferring protection across generations, from mother to nursing infant. So this is a cool information network and all, but how can we use it to our advantage? What can it do for us? Well, one way is by using it to design better, more effective vaccines. Let's take norovirus as an example. Norovirus is a nasty intestinal pathogen. It causes profuse vomiting and diarrhea, and I'm pretty sure most of the people in this room have had it before. Despite this, and despite the fact that it kills up to 200,000 people each year, we still have no licensed vaccine. And even worse, the vaccine candidates currently in clinical trials are performing suboptimally. Vaccines work in part because they get your immune system to produce proteins called antibodies that can bind directly to pathogens and stop them from infecting our cells. During my PhD, I discovered that a special type of antibody that can get into the gut was 100% protective against norovirus infection. But when those same antibodies were present in the body, in the blood, but couldn't get into the gut, the virus was able to infect the animals just fine. I give you this example to highlight the fact that for certain pathogens, and especially for very infectious ones, the entire battle is won or lost at the mucosal surface. So we need to make vaccines that elicit strong immunity at these sites, right? Well, actually, that's a pretty big problem for vaccine design. You're probably used to vaccines that look like this. They come in the form of a shot. And this is a really advantageous platform for a number of reasons. You're delivering the vaccine straight to the insides of your body, so your immune system is primed for strength and very alert. It's as if your immune cells got home one day and found an intruder already inside of their house. But there's a catch. Immune responses that are well poised to protect your insides don't usually do a good job of protecting your mucosal sites. So how can we get good immunity in the mucosa? You might think to yourself, why don't we just deliver the vaccine straight to the mucosal site? For example, we could use a pill to give a vaccine to the gut. That sounds like a good idea, but there's an issue. Mucosal sites, as I mentioned earlier, are constantly seeing the outside world, which means that they're constantly in contact with lots of fairly benign things. For example, your gut sees food, good bacteria, and even pieces of your own tissues. As a result, your intestines are very tolerant and very slow to launch strong immune responses. Because if they do it against the wrong thing, this can lead to real issues like allergy or inflammatory bowel disease. In other words, giving a vaccine straight to your gut might not really induce a strong response. So we've circled back to the same problem. How do we induce good mucosal immunity? Well, what if we took advantage of that information network? What if we took advantage of the fact that the immune system is so spatialized? We could start by priming the immune system for strength by injecting the vaccine straight into your insides, and then boost to the mucosa to tell the immune cells where they should be. This so-called prime and push vaccination strategy is actually a cutting-edge technique that researchers right here at Yale are currently investigating in a wide variety of diseases. Okay, I took some time to tell you about how your immune cells communicate with each other to develop different types of immune responses in the different spaces of your body. But the communication doesn't end there. Your immune cells can also talk to the other cells in your body, like your neurons in your brain. For example, have you ever noticed how when you get sick, you sometimes lose your appetite? It turns out that your immune cells can actually talk to your brain to cut your appetite down. But why would they want to do this? Shouldn't you want to eat more, have more energy to fight off the infection? As it turns out, scientists have found that mice that eat less food during certain bacterial infections actually have a greater chance of survival. But this talk between your brain and your immune system doesn't just go one way. Your brain also influences immunity. For example, in the lung, pain-sensing neurons can actually restrain the immune response to viral infections like flu, thereby making sure that your immune system doesn't go too crazy in the name of getting the virus out. In mice lacking these pain-sensing neurons, the virus replicates exactly the same, but the damage to the lung is much worse, and survival drops. This really shows you that your brain acts as an emergency brake on your immune system to remind it that we are playing on home turf. Okay, so your immune cells talk to themselves and to all of the other cells in your body. But what if I told you that that communication actually transcends species? You might not be aware of this, but right now you're covered in bacteria, both your outsides and your insides. And the conversations that these bacteria are having with your immune system are critical not just for your physical health, but also your mental health. In the last decade, scientists have really come to appreciate that inflammation within our bodies, and especially within our intestines, can cause serious damage to our minds, leading to increases in anxiety and depression-like behaviors in mice, and correlating with these in humans as well. What's even crazier is that scientists have found when you do a fecal matter transplant from a healthy mouse to a sick mouse, you can alleviate these anxiety-driven symptoms. But what does a poop smoothie have to do with making a mice feel better? Well, when you're doing a fecal matter transplant, you're not just transferring poop. And the answer has something to do with what we call the gut-brain axis. This is a catch-all term that scientists use to refer to the bundle of nerves, neurons, immune cells, hormones that connect your central nervous system to your gut. When you transfer the poop, there are tons of bacteria in it, the chemicals they make, immune factors, etc. And we know that all of these factors have an important role in promoting mental health. So when you take the poop from a healthy donor, it's kind of like liquid gold. Certain classes of good bacteria can chew up the foods we eat to make essential byproducts that we need. And thereby, they can promote the generation of good molecules that make us happy, and depress the generation of sad molecules that make us stressed. So all of the components of your body have an important part in getting your bacterial colonies in your gut to be happy. For example, your immune system plays a big role because it chooses which bacteria are allowed to be there and which bacteria get kicked out. But your brain also plays a really key role. The bacteria in your gut eat what you eat, and your brain decides what you eat. By feeding the good bacteria in your gut, you can help them expand and even foster a happier mind. So the next time you say no to McDonald's and have a salad instead, you can imagine your gut microbes jumping for joy. So all of these findings together really highlight the fact that there's been a fundamental shift in how we understand the immune system. Rather than being something that fights off illness, we've realized that the immune system is actually transmitting ideas between cells and between species all within your body. By fostering a happier bacterial family, you can foster a happier and less inflamed immune system, and in turn, foster a happier mind. Thanks to decades of basic research, we are now extremely well poised to take advantage of the fact that this immune system is an information network. We can exploit the compartmentalization to make better site-specific vaccines. We can use the fact that the immune system communicates with the central nervous system to use neurons as targets for traditional immune therapies against things like cancer or chronic illness. We can even make use of these findings in our everyday lives. For example, by eating good foods that have a lot of fiber and other nutrients, you can actually make a small but important step towards helping your mental health. It's clear that we still have so much left to learn. But what's even clearer is that the more we understand the hidden connections within our immune system, and the more we learn to control them, the better and more precisely we can affect human health. Thank you.